right, guys. Today's lecture is for crystal plasticity. So in crystal plasticity, basically, we wanna predict the macroscopic stress and strain response with microscopic features with the increment of strain. So how we do macroscopic stress strain curve, how we gonna get stress and strain, what we do to get stress strain graph. Basically, any kind of property can be done, can be get with testing, right? Testing, we do tensile testing. We have grips. We put our materials like the tensile tester. This is the material. We apply loading. We can control either stress or strain. This is the metal with the initial length of L0. We measure the elongation with strain gauge or extensometer. This is for elongation. We gauge it. And we also measure the force with force sensor. With the force cell, we can measure the force. Then we have force versus displacement. And we can convert force into stress and strain. We have elastic region and the plastic region. This is the yield stress. With crystal plasticity, we calculated the stress one by one with increments with elastic strain. Then we try to get this form. But this is macroscopic, and crystal plasticity, we include microscopic features. What are the microscopic features that comes into your mind? Any idea in the microscopic feature, Furkan? Sorry, Resul?
Grain size, can we say that, hocam?
Maybe grain size, right? Grain size, dislocation density, etc. Macroscopic features, we just displace the material, we pull down till fracture, and the input parameters are temperature is one parameter, strain rate, it is constant during the tensile test is another parameter. Of course, we have instant displacement as a function of time. And this strain rate represents how quickly we are stretching the material. And temperature times the strain rate will give us dlt L0, which is meter, the initial length, dt. So this is the experimental condition. And the material-related parameters, are shear modulus, Poisson's ratio, elastic modulus, Berger's vector, initial dislocation density, maybe direct coefficient, right? These are all initial material constants. So how we get these points with crystal plasticity? First, the first step is we assume total strain is equal to elastic strain plus plastic strain, right? It's a reasonable assumption. If you go there and check at this point, for example, we have elastic strain plus plastic strain, which gives us the total strain. Then if you take the derivative of both hand sides, you will get dE is equal to total strain derivative, elastic strain, plus d plastic strain, which is equal to the initial strain rate times dt. This is elastic, and this is plastic strain. And the thing is, we need to calculate elastic and plastic strains. How we can calculate, how we can define plastic strain? Any idea how we can find the epsilon plastic? Think about the slip. So let's try to define it not by formula, but with what is the physics behind it? We need some slip, and we have certain amount of slip plane and directions. So plastic strain is summation of all slip systems. Let's define alpha as a slip system. You know, in FCC, we have 12 slip system. In BCC, we have 48 slip system. We already know it. So for each slip system, from 1 to n, till whatever we have, we just need to sum the amount of slip in each slip system, right? Due to the dislocation glide. So this is the amount of slip in each slip system alpha due to dislocation glide. Perfect. So this is for FCC, alpha goes from 1 to 12. And we have planes and direction, right? Alpha, we have 1, 2 till 12. So what is the slip plane in FCC? What's the plane?
1, 1, 1 plane.
Always 1, 1, 1, right? 1, 1, 1. We can have, of course, one. This is the family. And what is the slip direction?
1, 1, 0.
Always the Burgers vector, the dislocation is 1, 1, 0. In total, we have 12 slip system. Perfect. So far, so good. Then we have the definition of plastic strain. And if you remember the Oravan equation, we can calculate the shear rate by Oravan equation. And without going to Oravan equation, maybe we can go one step forward and define what is this in terms of formula. So d epsilon p is equal to, from alpha is equal to 1 to n, whatever it is, the amount of slip in each slip system we are saying. So which corresponds, we need shear rate, which is gamma prime, each slip system. And due to the dislocation glide, so dislocation density corresponds to dislocation glide. So this is the formula. This is the important formula for d epsilon p. Remember, we're gonna calculate this one, and we are trying to find d epsilon p, which is just shear rate times the dislocation density. And how we can calculate the shear rate? If you recall, Orovan's equation, the shear rate gamma prime, each slip system can be calculated through the dislocation density, each slip system. So this is, don't forget, slip system. Dislocation density times the Burgers vector. So Burgers vector in FCC, we have only one type of Burgers vector, right? Which is 1/2, 1, 1, 0 for FCC. And the velocity. This is the velocity of dislocation. So if we can calculate this one, we can calculate the plastic strain rate. And let's check the units. What is the unit of dislocation density? Roa, do you remember the unit of dislocation density?
No, I cannot remember.
Anyone who remembers the unit of dislocation density? It is basically like dislocation per unit meter, right? Then it is meter to 1/meter square. It is the 1/area. And what is the unit of Burgers vector? Ahmet Hakan?
I don't remember hocam. Does it have a unit?
It should have a unit, right? The Burgers vector, we have some slip in atoms. What is the unit of Burgers vector, it is just the length, right? Meter. And what is the unit of velocity? Ramazan, what is the unit of velocity?
Meter per second.
Perfect. Meter per second. So the shear rate unit, meters just cancel out, is 1/second. Perfect. So how can we calculate these values? Let's start with dislocation density. Dislocation density at each slip system. So dislocation density, actually it changes as the displacement takes place, right? During the deformation, the dislocation density evolves. And instead of calculating the dislocation density, I wanna calculate the derivative of dislocation density. So this dot represents the derivative with respect to the time, because the dislocation density changes with respect to time. All right, the dislocation density. During deformation, we create some dislocation, we distract some dislocation, they annihilate each other. And generally, we have one term due to creation and multiplication with the constant of K1, dislocation density, let's say alpha, minus, we need to subtract the distraction terms once we have annihilation, K2, and dislocation density square times the shear rate. This is the formula for dislocation density. And generally, since we are evolving the dislocation density, we are creating more dislocation. K1 should be greater than K2, right? So this term, this whole term is for creation of dislocation and multiplication. And this term is for distraction. Annihilation. And K1 generally greater than K2. So we are evolving dislocations. And the initial dislocation density at T is equal to 0. We represent it as initial dislocation density. All right, so we will find dislocation density with this formula. B is given, so how about velocity of dislocation? Velocity of dislocation, all right. Once the resolved shear stress is greater than the lattice resistance, right? We have dislocation moment. Dislocation moves. If lattice resistance is, of course, if vice versa, resolved shear stress is less than the lattice resistance, we don't have any velocity. But if it is greater than the lattice resistance, which is very low for FCC, maybe 5 megapascal, 10 megapascal, maybe 40 megapascal, depending on the FCC material. we have velocity. And velocity can be calculated through the Burgers vector times the shear stress at each slip system always divided by the direct coefficient. And this direct coefficient is a function of sometimes temperature, sometimes if you have additional solutes in your material, C, and we have a B0 plus tau B1. And if you go ahead and check some papers, you will see that it is at the order of 10 to the -4. All right. How about the excess stress? How can we calculate this value? What is the excess stress? The excess stress, delta tau alpha, is resolve shear stress each slip system minus we need to subtract the resistance of the glide plane, right? The back stress or the resistance. Let's call it with G. This is the resistance of each glide plane. All right. This value, we can calculate. This value is important. This value, we calculated through dislocation density times the Burgers vector, not Burgers vector, sorry, the shear tensor, let's call it shear tensor. This is the shear tensor. Sorry, stress tensor. Times N. And we know what is N, the plane. For FCC, we only have 111 plane. So once we solve this, we can calculate this value. How about the resistance? Resistance, we know we have one material constant, right? We have the lattice resistance, the peerless stress. So it is tau 0. This is the peerless stress. About my handwriting. What can cause resistance? What else? Actually, we covered the topics. What causes dislocation to stop? The hardening mechanisms, right? We need to add each and every hardening mechanism. For example, solute solution hardening. We had one constant and it was linearly proportional with C, the concentration, and epsilon 3.2. grain boundary hardening, right? It is related to mean free path of dislocation, and precipitation hardening, which is L minus 2R. Then you need to add all sorts of hardening. Of course, the strain hardening can be calculated through alpha mu b square root of dislocation density. Once we add all of these value, we calculate the resistance of each glide plane. So if we add more strengthening, we are increasing to G. So if we produce more dislocation, for example, we are increasing the dislocation density, or if we add more solute, we are increasing the solute solution strengthening effect, then we are increasing the resistance of each plane. In order to overcome this resistance of each plane, we have to increase our result shear stress, right? Then we have strengthening. So that is the mechanism. So if we add, let me write, if adding more strengthening mechanism, we basically increase the G, the resistance of each plane. Then the result shear stress of alpha has to increase as well in order to overcome, in order to strengthening. Then applied stress needs to goes up, and the stress tensor should increase. The applied stress tensor should increase in order to increase the resolve shear stress. Any questions so far, guys?
No hocam.
Any question? Roa?
So far clear hocam.
So this is very good point. Think about ceramics. I'll just open a very small parenthesis. Normally we are dealing with metals, but I want to point out ceramics at this point. Ceramic materials, the stress tensor is less than this tau. So the resistance, lattice resistance is too large for ceramic. Ceramic materials. So this location exists and move only when you apply a lot of stress. And once you apply a lot of stress, you activate this location, you are increasing your G, you're increasing your tau, result shear stress, then you need to increase your stress tensor, which becomes the material more ductile. But in ceramics, since lattice resistance is too high and the stress tensor cannot exceed the lattice resistance, we see this material is brittle. If we don't see any increase, if we don't see, we cannot exit the barrier, then that's a problem. But think about the dislocation hardening. Think about the strain hardening. If it becomes larger, if we increase the amount of dislocation density, basically dislocation density, the strain hardening is proportional with the dislocation density. And once we increase dislocation density, we are actually making this resistance greater, right? Then we are basically increasing the strength of a material. For example, cold working. We are increasing the resistance, and the stress should also increase. So far, so good. So, sorry, let's delete this page. The thing is, we have to calculate the stress tensor. At this point, let's assume linear elasticity. And linear elasticity is valid till the core of dislocation, so it's a good assumption. And Hooke's law is valid, right? The stress tensor is nothing but the modulus tensor, C or K, you can call whatever you want, times the strain tensor, elastic strain tensor. So this is the strain. So guys, the question is, which strain is this? Which strain is responsible for strengthening? Which strain we use to calculate stress? Is it elastic strain or plastic strain? Which one creates the strengthening in the material?
Plastic strain hocam.
Resul is suggesting plastic strain. Any other example? Any other idea? We said the epsilon is equal to the elastic plus the plastic, which is equal to strain rate times dt, which is constant. If you think about the stress and strain curve, once you have, for example, you are going from here to here, you have elastic stress, strain plus plastic strain. Till this point, we only have elastic stress. And at this point, we have some elastic recovery. This is the elastic recovery, and this part is the plastic strain. But for this much strengthening, just think about these two. Only the elastic strain corresponds to stress. The plastic strain has nothing to do with stress. It has no contribution to the stress. So we need to deal with the elastic strain. So this plastic strain, sorry, I forgot D here. This has no contribution to stress. In elastic regime, you only have elastic stress. Then once you multiply it with E, you can calculate sigma. But in plastic region, we have both elastic and plastic strain. Due to the contribution of plastic strain, the elastic strain decreases, and we see some decrease in the stress-strain response. So basically, the stress tensor is just modulus tensor times the elastic strain tensor. This is very important. We need to find the elastic strain tensor. So with crystal plasticity, we will do self-consistent iterative process. Self-iterative process. If you look at the data here, what we know is delta epsilon. We know delta epsilon in every step, right? These are all delta epsilons. This is delta epsilon from here to here. We know what is delta epsilon. And what we want to know is actually this guy right here, right? We want to know the elastic strain. So firstly, let me write, we know what is the epsilon. In order to create self-consistent iterative process, we will assume a value for dE. So we know this one, and we will assume this guy. Then we can calculate this guy right here. Perfect. The first step. So this is the iterative process. You need to choose the epsilon, which is less than the epsilon. Then the second, from this formula, we can get plastic strain derivative. The epsilon plastic can be calculated through the total strain, which is known, then the epsilon that we assumed. So we have two conditions. Third, what is the increment of stress? What is d sigma? It is just the Young's modulus times the epsilon is the sigma, right? And we just calculate the d sigma. How can we calculate the total stress? Total stress. So at each step, Let me go back here. Suppose you calculated d sigma. In order to calculate the total stress, you need to add the previous stress, which is this stress, to d sigma. To calculate this stress, you need to add the previous stress to the incremental stress. So the total stress at the time of t is nothing but the stress at the previous step, t minus 1, plus the increment, d sigma. And how can we calculate this guy, this stress tensor? Actually, we have the formula for that guy. Let's go back. Yeah, torsional shear stress is equal to this stress tensor. We can get this stress tensor from this equation. This is the same stress tensor. We use this stress tensor here. All right, so let's start from the beginning. When the stress is small, when stress is very small stress, let's start with this graph. Stress versus strain. We start with 0 and 0. Then we have linear relation. We go to the second point. We go to the third point, and the slope is just modulus of elasticity. When the stress is little, we have linear relationship. All right. If delta tau alpha is greater than 0, then the velocity, we know the velocity. Where is the formula? All right, let's go back here. If the result shear stress is less than the lattice resistance, the velocity is 0. If the velocity is 0, then we don't have any shear rate, right? If we don't have any shear rate, we don't have any plastic strain, then the E is only the elastic strain, correct? Then we have just a linear relationship. Does that make sense? Let's do it again. So we are in the elastic region, and the lattice resistance is greater than result shear stress. So we are at this point. Then we don't have any velocity. If we don't have any velocity, if the velocity is 0, then we don't get any shear rate. If we don't have any shear, that means we don't have any plastic strain, and the total strain, if we don't have any plastic strain, the total strain is only elastic strain. So this term, the plastic strain will be equal to 0, then we will have only elastic strain. So we have only linear relation. All right. Then what happens when we have velocity? Once we exit, where is it? Sorry. Once we exit the lattice resistance, then we have velocity. We need to use this formula. Let me go there. The velocity of alpha is equal to tau b over b. B times to alpha divided by the Dirac coefficient. And recall the epsilon p is equal to, from I1 to n, shear rate alpha times the dislocation density. Then, of course, we have, let me go to the second page. The epsilon p is equal to total strain minus the elastic strain. And this is also I is from 1 to, or let's say alpha, it's from 1 to n, all amount of slip at each slip system due to dislocation glide. You can just compare these two equations. If these two do not match, you need to go back to the first step. Once we have this equation, then we have plastic strain. Then, since the epsilon is constant, this is constant, right? For each step, we are controlling the epsilon. The epsilon is constant. And once we have plastic strain, the elastic strain becomes smaller, correct? Then we create, all right, let's go. We only have elastic strain. Once we bend here, the epsilon becomes smaller, E becomes smaller. Once we have smaller elastic strain, we will get less stress. Then once we have less stress, we will bend the curve. So here it bends. Guys, does that make sense? This step. Once we have plastic strain, we are getting less elastic strain, then we have less this value, the incremental stress.
But then when you say we get less incremental stress, does it
Yes.
mean that the value of the stress is like decreasing, or it's not increasing in the same rate, or what do you mean exactly?
But it's not increasing in the same rate, because the stress at the time being is the summation of previous stress plus the incremental stress, right? And the incremental stress is just the elastic strain times the modulus. And we are fixing the total strain. Since we have plastic strain, we are decreasing the elastic strain. Then we are decreasing the incremental stress. All right, here we have, so this is the stress T minus 1. And the incremental stress is sigma at T. The sigma at T is less than the sigma T minus 1. Since we have less elastic strain. Questions? So we are at this point. Now we have some resistance. We have some G. This is very important. We have some G. And the G alpha is just the lattice resistance plus the strain hardening contribution plus solute solution strengthening with square root of C plus all the other terms. All right. So how we actually proceed with the crystal plasticity? Let me just summarize it again in a better way. Step 1. Maybe I can just go to new slides and bend the screen. Step 1. Let me try to do it again. We need to choose the elastic strain. I want to choose elastic strain. This is the first step. And we know what is elastic strain. Then we can calculate plastic strain is equal to strain rate times T minus the elastic strain. Step 2 is calculate the stress. Stress, the incremental stress, is proportional with the elastic strain. Plastic strain has nothing to do with it. So we have the stiffness tensor times the increment of this elastic strain. This guy right here. Step 3. This is important, guys. We need to calculate the excess stress. Delta tau alpha. If the excess stress is less than 0, then you need to go back to first step, step 1. Else is actually step 4. where we have delta tau excess stress is greater than 0, then calculate the speed, the shear rate, and the dislocation density. You have all the formulations in the previous slide. And step 5, if we know these two, we can calculate the plastic strain. So if we calculate the plastic strain, go to step 6. So here at step 1, we have one plastic strain. And here we have another plastic strain. Just compare them. If the plastic strain that we calculate at step 5 is equal to the plastic strain that we calculate at 1, all right, we can go to the next step. Then we are successful. If not, what should we do? We need to choose different elastic strain. Choose different elastic strain and follow the same procedure. Go back to the step number 2 till you converge, till your stress strain curve converges. All right, so maybe we can just go ahead and check. We are at step number 1. We just choose one elastic strain. Let me go to the new page. How can I add another page? Let me check. Stress versus strain. We always start the same location and we always fix, don't forget fix the epsilon, which is the epsilon elastic and the epsilon plastic. Here, first step, you just choose an elastic strain epsilon 0. Then once you check your tau, you calculate your tau, right? You need to calculate this excess stress. Till the lattice resistance, till we get positive values, we are in the elastic region. But before that, we only have elastic stress, elastic strain. Then our tau RSS is less than lattice resistance. So we are at this region. Once you calculate your excess stress, you see that in the elastic region, the lattice resistance is greater than your tau RSS. And you can calculate your RSS from this formula. Once it is 0, then your velocity is 0. If your velocity is 0, then basically your shear rate is 0. If your shear rate is 0, you don't have any plastic strain, then what d epsilon is equal to, in the second step, the epsilon is equal to only elastic strain. Till at the second stage also, you calculate the stress, and you see that it is less than lattice resistance, then you don't have any velocity, then your plastic strain is 0, and the fixed amount of strain, the epsilon, is equal to only elastic strain. Then you calculate the excess stress. Excess stress is just elastic strain times the Young's modulus. Then you just add this excess strain on top of the previous strain till some point, all right, here, let's say you also get this point, all right? The next step is calculate the stress again. You calculate your excess stress, all right? So you have these two conditions. Once your excess stress is less than 0, you need to go back to the elastic strain part. Then you just calculate the stress. But once your excess stress is greater than 0, then you need to calculate these values. Then if it is greater than 0, that means the velocity is not equal to 0. Then you need to calculate your velocity through this equation. You need to calculate your dislocation density. You need to calculate your shear rate. Dislocation density can be calculated through here. Then you calculate your shear rate. You have this value. Now, here you're fixing your strain again. So the epsilon is always same. The epsilon is same. But now you have plastic strain. And what is the sigma? It is just the elastic strain times plus the stress at T minus 1, right? You can just delete this one. Then what is elastic strain here? Total strain minus the epsilon plastic. Since we have plastic strain right now, we are decreasing our elastic strain. Then once you multiply this decreased value with Young's modulus, you will get a less value than previous value. Then the curve will be bent like this. And it will go like this till we have some point. Maybe after certain amount, due to work hardening, you can also get an additional increase due to work hardening. But that is the procedure that you need to follow in crystal plasticity. Basically, you just choose one elastic strain, you calculate stress, then you calculate the excess stress. If it is less than 0, you're in elastic range. You just need to go back to step number 1. If your excess stress is greater than 0, you need to calculate your velocity of dislocation, the dislocation density, and shear rate. Once you know your shear rate and dislocation density, you can calculate your basically plastic strain. Once you calculate your plastic strain, you can just compare that the one that you selected is a plastic strain and the one you calculated. If they converge, if they are equal to each other, then you're good to go. If not, you need to choose another elastic strain. Any question, guys, related to this procedure? If not, I'll just take a break at this point.